Okay, good afternoon everyone. Welcome back from afternoon tea. It's my pleasure this afternoon to introduce Kim Carter. Kim Carter, as the author of a few security books, organiser of the Christchurch Hacker Conference, otherwise known as CHICON, is helping organise OWASP Day in Auckland with me, and all-round nice fellow. Today he'll be talking about the art of exploitation. So let's welcome Kim to the stage.
How's it going, everyone? So we're going to look at the most effective attack techniques for the most common vulnerabilities. So what are the most common vulnerabilities? So this is a recent cryptogram reading, which is Dan Hennage reading out Bruce Snyer's blog posts. Can we hear that?
Credential. Basically, they steal hackers break into networks is by stealing and using a valid credential. Basically, they steal passwords, set up man-in-the-middle attacks to piggyback on legitimate logins, or engage in cleverer attacks to masquerade as authorized users. It's a more effective avenue of attack in many ways. It doesn't involve finding a zero-day or unpatched vulnerability. There's less chance of discovery, and it gives the attacker more flexibility in technique. Rob Joyce, the head of the NSA's Tailored Access Operations.
So that's password stealing. Steve Miller, which is the head of security operations for FireEye, formerly worked for NSA. This is a wee clip from him from Risky Business.
So most of the attackers I see use the very common attack vectors: spear phishing, web shells. Very rarely are exploits even necessary to get into their target environments. I've seen an increasing use in certainly in things like LinkedIn and Facebook, sort of targeting of specific individuals for attackers to get in. So, for me in my job, I always worry about looking at weaponized documents like resumes and stuff, because I do a lot of hiring now. I look at hundreds of resumes a year, and very, very common attacker technique that will probably be pervasive forever.
Okay, so let's start with passwords. So there's so many ways to get passwords. We can brute force databases that have used simple hashing or key derivation functions with few iterations. We can brute force web UIs. We can use any of the many password profiling tools available to us. Or we can go phishing for them. So we're also going to use the browser exploitation framework, also known as BEEF, which is similar to a web shell but better because nothing's dropped on the target box. So there's no issues with antivirus. And we're going to use a module that acts as a Facebook login prompt. I decided to lump all these attacks into a simple single attack so that we have time for the second half of this talk. So let's see how this is played out. Just resizing a window so that it'll actually fit on this screen. Okay, so first of all we start Metasploit. It's not necessary in this demo, but if you want to use the Metasploit modules via BEEF, you'll have to have it running. And then we start BEEF. Okay, so that's the browser exploitation framework administrative UI. So we're just logging into that as the attacker. Okay, so this is NodeGoat. This is a purposely vulnerable Node web application. It's an OWASP project. So we've just logged in there as a low privileged user. And we're just going to go to the profile route and dropped a script tag into the last name. All of these 7 fields here are vulnerable to basically dropping in script tags and that sort of thing, because they're not validated, sanitized. Yeah. So basically what we're going to do there is we're just going to drop in the hook.js file, which is the piece of JavaScript which calls up the Beef communication server and continually asks for commands to be executed on the post-exploited victim. So now the administrator's logging in, which is our target. And you can see there, if we just go back a little bit, yeah, so the last name field there for, is it? The top one anyway, I can't quite see it. Yep, so that's got our script tag in it, and that's now executed. So that's hooked the browser, and you can see the IP address there of the hook browser, and you can see the hooks continuing to poll in the network tab of the developer tools. So if you mouse over the victim's IP address there, you get quite a bit of information on the actual victim there. And you've got quite a few tabs across the top there too, which also gives quite a bit of information. So what we're going to do here is we're just going to spring a pretty simple attack based on some reconnaissance that we've done. We know that the victim lives on Facebook, and we're just going to pop a modal dialog box here. So this modal dialog box could be any social media modal, basically, that so basically it just captures credentials, and because it's modal, a user can't move away from it until they've actually entered something. So I'm using a Facebook one in this stage because we've done some recon on them, and we know that they use Facebook regularly. So the victim enters lazydev at targeted.com and lazydev for a password. That's L4ZYDEV. And that's their credentials there. So we've now got their credentials. And we're just going to have a bit of a quick look through some of the modules available in Beef. As you can see, there's a plethora of them. So all of those are exploits that we can carry out. Yeah, those are the Metasploit ones there. Okay. So all of this is basically just because of the trivial cross-site scripting defect. It really is trivial, but because of that, we can steal passwords. As you can see, we've done some spear phishing, kind of web shells, and Facebook. Facebook. Yeah. So now we're going to have a go at weaponized documents. So we're going to use a PowerShell attack. And by default, PowerShell is installed on Windows Server 2008 R2 and Windows 7 onwards. PowerShell is going to continue to be on all boxes, providing access to pretty much everything on the box. So this is excellent news for penetration testers and other attackers. Execution policies are easily overridden. And we've got full direct access to the Win32 API and the .NET framework. And we can assemble malicious shellcode in memory without antivirus detecting it. So we're going to be using libraries PSM-SF, Powersploit, and Nishing. PSM-SF gives us a Metasploit resource file that we can use to listen from the attacking machine. And it also will dish us up with a PowerShell _hacking.bat, which is basically a reverse TCP shellcode embedded into a PowerShell script that overwrites the calling instance of PowerShell with the reverse TCP shellcode, and then invokes it, which contacts the attacker's listener. And we also host the PowerShell_hacking.bat as payload.txt, just so that you can see in the demo the difference. And we use PowerSploit for adding persistence, and Nishang for generating the actual Office document virus. Okay, so this is the sequence diagram for how the attack plays out and how the parts are basically built up. Don't stress too much about that because I'm going to be walking through the demo and explaining it as we go. So we create a weaponized document that downloads and invokes encoded persistent script.ps1. So that's your encoded persistent script.ps1 down there, which is the encoded version of persistence.ps1. Now we can see in here there's also some base64 encoded script in here. This here is taken directly from persistent fetch run payload.ps1. So all that file does is it downloads and executes the hosted payload.txt, which we create previously. And that's the part that actually overwrites the calling instance of PowerShell with a reverse TCP shell, creates a thread, and then invokes the thread. So it's overwriting the calling instance of PowerShell. So if we go back down to here, and we look at persistence.ps1, which ends up being encoded to encoded persistence PS1, we've got, so I've explained that. Then we've got these two sections here. So the first one, basically, it creates a scheduled task that runs hourly, and it sets up PowerShell to run on the hour. Same as this one down here, but the top one's for an administrator. This one here is for a low-privileged user. So if the virus is run by an administrative user, then it sets up the scheduled task as an admin. Otherwise, it's as a low-privileged user, which runs the PowerShell profile, and we've basically got this base64 encoded part, which pulls down the payload.txt, written to the PowerShell profile. That's what happens there. Okay, so let's see how this actually plays out too. Just going to drag this over here because I think it's going to go really big. Okay, so first up we import the PowerSploit persistence module. And then we import the PowerSploit script modification module, which we use to encode the persistence.ps1 to the encoded persistent script.ps1. So that's, if we look back here, so that's encoding this top block into this base64 encoded block. Okay, so that's that. Then we need to bring into scope elevated persistence and user persistence options, which create those two parts, those two separate parts, right? So there's one for the administrator and then one for low privileged user. So either one of those will get run depending on whether the user that runs the virus is an administrator or a low privileged user. Okay, so that's those two. Cool. Okay, so that is, as you've seen before, that's the persistence fetch run payload.ps1. Yeah, so we're going to add persistence here to our Office document. We're using persistent fetch run payload. Yeah, so we're adding that to it. And then we've got the elevated persistence option and the low privilege option there as well. And then our out file. So that's actually creating our Office. No, it's not creating our Office document. Okay, so what's that doing? That is now creating encoded persistent script and this one up here, which feeds into the encoded persistent script. And that's what it looks like, just like you saw in the book. Okay, so we've already got payload.txt hosted from a previous play. That's also in the book, but you haven't seen that. And now we need to host encoded persistent script and then start our web server if it's not already running. So this is, in my case, it's just hosted on the attack box. It could be hosted anywhere. So the encoded persistent script gets run first, which pulls down the payload.txt hourly once the scheduled task is set up. Yep, so now we're creating our actual virus, our Office document, and we're feeding in the encoded persistent script, which sets up the persistence. And there it is there, that's our actual virus. And we just added basically some dummy HTML for the CHM, so when the user opens it, they think, oh yeah, that's kind of what I expected. So now we need to run Metasploit on the attacker's box with the PowerShell_MSFRC resource file that I created in a previous demo, which you haven't seen, but that's all that's in it, what you're seeing there at the top. And that will catch the reverse shell once the target runs the doc.chm and persistent fetch run payload, which downloads and invokes the payload.txt every hour with the scheduled task. Okay, so we're running Metasploit here, so we're listening for our reverse TCP shell on the hour, every hour. Okay, so now you've got to get your virus into your target's position. And basically what we're doing here was just, we're doing a little bit of work now just on the same environment that our target's going to be on. So it's on a Windows box. Yep, so we're just showing there that there's currently no PowerShell profile, and we don't currently have a scheduled task called updater, which is the scheduled task that simply runs PowerShell. So now the target runs our virus, which downloads and invokes the encoded persistent script, which sets up the persistent just to run PowerShell, and it also adds that script that pulls down the payload to our PowerShell profile. Because the PowerShell profile, whatever's in the PowerShell profile always gets run first when you first start PowerShell. And because the payload that gets pulled down in the secondary part overwrites the calling instance of PowerShell with the reverse TCP shellcode, then we're all set up and ready to go. Okay, so our target's now running our payload, running the virus. That's set up our persistence. And as you can see, we've got a Windows PowerShell profile there. So we'll cd into that directory and have a look at the actual profile, the profile file. And you'll see the target's actually got the script here, right? So the encoded script is in the PowerShell profile, and the encoded version is what you're seeing there as the IEX new object, a net.web client which downloads and invokes the payload.txt. And if we refresh the scheduled tasks, we've now got our updater scheduled task, which just runs PowerShell on the hour. Okay, so now we're waiting for our scheduled task to run. And that's it. So that will run every hour, and it survives reboots and most other user interactions. And we can stop and start our listener. There's no problem with that. It'll still phone home every hour. And that's it. Basically, we've got our session. Okay. Okay, so the Power exploit persistence module offers persistence techniques, permanent WMI, scheduled task as you've just seen, and a registry. And at the following stages, at login, at startup, on idle, daily, hourly as we've just seen, or at any specified time you want to add in there. So that covers weaponized documents. Let's look at some mitigations. So in the case of the vulnerability, this vulnerability, so this was a simple cross-site scripting vulnerability, a stored cross-site scripting vulnerability. So the input wasn't validated, filtered, or sanitized. So in the Web Applications chapter of my book, I go over what validation is, what filtering is, what sanitization is, and then there's the actual countermeasures, which again I discuss what they are and how they affect you, and then there's sample codes and that sort of thing, so you can get yourself out of that mess. Okay, so for weaponized documents, network intrusion detection systems can recognize reverse shells flying across your network, so that's one countermeasure. Standard antivirus doesn't work. Next-gen antivirus is working, but that's next-gen as in a next-gen antivirus with machine learning. Know the origin of everything you want to run and stop being so trusting. Everything in this world has a potential to blow up in your face. Always be suspicious and paranoid. So we've seen exploitation and we've seen mitigation. So now I need to work out how to get both of these to fit within your sprints. Now, I can hear you saying, we don't want these in our sprints, we just want a code, right? But bear with me and you'll see why you want them in your sprints. So we first need to understand our attackers and what their workflow looks like. In order to beat your enemy, you must understand your enemy. So in my book, I work through the process that your attacker is very likely to take. And yeah, so basically their workflow. And I've got heaps of hands-on examples and that sort of thing about how they're going to attack you. The 5 stages of attacker are all covered in there. So we then take what we've learned from the red team and create a set of development-related processes and practices, which we then apply to your Scrum team, also known as the blue team in security speak, or your other defending team. That's educating and empowering you. We bring the security focus from the most expensive place, that's late in the software development lifecycle, often retrofitted or bolted on, to the least expensive place within each sprint as part of your definition of done. We augment your Scrum process with security-focused processes and practices. So on the right, we've got your Scrum artifacts, transparency, and events. On the left is the additional security-focused processes and practices that we add. So here's the kicker. By doing this, we drastically reduce the cost of finding not just security defects, but all defects. This is the average cost of fixing defects based on when they're introduced versus when they're detected. Putting the practices, that's finding the defects in the right order, can reduce costs by up to 100 times. So what we've got there is, in the construction phase, if you find and fix a defect in post-release, it's going to cost you 10 to 25 times the cost that it would have costed you if you found and fixed it as you introduced it. And similar sorts of things there you see in the requirements and architecture stage, but they're more costly because they're earlier on, and there's been more things built on top of it. So the idea is to detect faults at the stage where they're least time-consuming and costly to correct. So what can we use to make this process of finding and fixing defects cheaper? So the following are some of the processes and practices I've found that are, when used together within Scrum teams, become a game changer. First thing, establish a security champion. So a security champion is a bit like a Scrum Master in that they're a servant leader and a mentor, but with the relevant security skills. If they haven't already got the relevant security skills, but they're keen to learn and they're pretty smart, then that still could be a pretty good fit for the security champion. So they must be a team member and not external. So many times I've seen within organisations you've got like sets of development teams and you've got a security team. So what happens here, right, is often you'll get a person from the security team come into the development team and sit with a developer for a while or something, possibly beat them over the head, or even nicely say to them, oh, look, you've got problems here, have you tried this, how about fixing this, have you tried fixing it this way, and that sort of thing. But just about always what I see is when they leave the team, the development team goes back to doing things the way they were, and because they are from the security team, they're considered an outsider. So the idea here is if you actually pick someone that's within the development team to take the role of the security champion, they've already got the team's respect, and they're always around the rest of the developers as well. So there's basically no getting away from them. And the idea is that the security champion can infect their passion and their smarts as they pick it up on the rest of the team. And also don't push the role onto them. Mandating roles doesn't work so well. The idea is to hold it up there and then get the individual to basically take it on themselves. So the security champion will be able to bring change to within the team and the organisation. Then we've got handcrafted penetration testing. So this is really costly when performed late in the development life cycle, but many times cheaper when performed within each sprint. Now, the security champion can help train the team members, and myself or another security pro can train the champion. And there's lots of guidance on how to do this in my book, and there's also BSIM, OWASP, Microsoft and Intel also have lots of guidance on how to do this. Peer programming. Two brains on your code is not just twice as good as one, especially when one has the security focus. Code reviews. You can augment your usual code review process with the likes of JS linting tools as part of your build and source control pre-commit if you're not already doing this. And there's a collection of static and dynamic analysis tools also listed in my book that you can use to automate. We cover techniques for asserting discipline in inherently undisciplined languages, such as JavaScript. We cover offerings like Flow, TypeScript, etc., which gives us static type checking, which is essentially the implementation of a design by contract. Measure cyclomatic complexity and reward those that reduce it. Then we move into consuming free and open source, which I think we're all doing, which is addressed by OWASP A9 of the top 10. That's using components with known vulnerabilities. So this is often not thoroughly tested or reviewed. It's often created by amateurs that can and do introduce vulnerabilities. It's also an effective attack vector for getting your malware into others' working systems. And it doesn't undergo the same requirements analysis, defining of scope, acceptance criteria, test conditions, and sign-off that our commercial software does. So you can implement process and governance around this. So you can set up the likes of our whitelisted, set up a whitelist so that the organisation knows that they're allowed to use specific libraries within their projects. Now this whitelisting process, it's got to be quite a fast-track sort of a process, because when developers are in a sprint and they want to consume a library and they realise that it's not in the whitelist, it needs to be fast-tracked quite quickly, because otherwise you're going to be blocking the team. So one idea I've thought of there is of having like a committee that actually is responsible for setting up the whitelist of consumable packages. So that potentially each person in that committee is assigned to a development team, so that when you've got your developers within a specific team working on a a backlog item, then they can actually go to the person within their team and say, oh, look, we haven't got this package, can we get it agreed and pulled into the whitelist? You can also set up an automated process running over your code, checking that no libraries are actually used in there that aren't in the whitelist, and other simple initiatives that I discuss in my book. Don't install Node.js the official way. Piping arbitrary scripts directly from the internet to your root shell is asking for trouble. The tooling landscape's starting to fill out. So we've got npm outdated, npm check. We've got David, which uses your package.json and provides a GitHub badge informing you of out-of-date or insecure packages. We've got retire.js, which has been around for quite a while. It can be run as part of your continuous integration. It's got a Chrome and a Firefox extension, a grunt and a gulp task, a burp and a zap plugin, and an online scanner. And we've also got the Node security platform, which has a command line interface, a gulp task, a code climate engine, and a GitHub pull request integration. And we've got Snike, which has a similar feature set to the Node security project with a few extras and a larger price tag, and some others. So when you usually run your test condition workshop, when the developer pulls a sprint backlog item into work in progress, you start thinking about what types of testing are going to be the most suitable. And developers create test conditions. Hopefully most of us have seen these. So your givens are your initial state of your system, your whens are changes to that initial state, usually performed by users, and your thens are just expected outcomes. Pretty simple stuff. They also create evil test conditions, which are the same, but just with the security focus. Now, often developers will struggle here because they won't be thinking like the attacker, and they struggle to think about how they can break their own systems. And that's where the likes of the security champion can sit with the developers in the test condition workshop and help them how to think like the attacker. So test conditions lead into TDD and BDD perfectly. Evil test conditions lead into security-focused TDD, BDD, just the same. TDD inherently creates testable code. Testable code is loosely coupled, easy to maintain, streamlines continuous delivery, allows us to make changes faster with confidence. If it's hard, it forces us to evaluate why it's hard and thus reduce code complexity. And inherently forces us to embrace many good architectural principles. And all with the added benefit of driving out security defects iteratively as the code's being written. Then into your continuous integration, which provides another continuous security check. Measure test speed and reward those that create fast-running tests. Traditionally, penetration testing and security in general is often thought about and performed at the end of a project. Unbelievably, often once the solution's delivered. Now imagine if you did this with any other form of QA. So the reason it's so expensive here, right, is because developers have got to get, so basically it could be days, it could be weeks, it could be months, even years in some case, since the defects were introduced to go live. Developers could have moved out of the team, like the team's changed, and those ones that are left have actually got to they've got to build up the picture in their mind of where the defect is. They've got to work out the layers around the defect and in other areas of the system that any potential changes to that defect could influence, and they've got to do all that. So that can take hours, sometimes even a day or more. So by converting that effort into something that's used in parallel with development, we significantly reduce the costs and lift the quality. So what we've done is we've moved the finding and fixing of defects from the end of the development lifecycle right down to where they're being introduced. So we're finding and fixing them as they're being introduced. And that's where we get that huge cost saving. So that brings us to security regression testing with the Zap API and NodeGoat. Some of you may have seen this demo before. It's a proof of concept. So there's two players in this. So we've got two OWASP projects. So we've got the Zap API and we've got NodeGoat. The idea is that you take this proof of concept and you swap out NodeGoat and then bring in your web application as the system under test. So the Zap API is an HTTP intercepting proxy with a large collection of known defects and a large collection of exploits for those defects. And it's got a RESTful interface that we can program against and basically just tell it how we want it to beat up our application. So a NodeGoat is the purposely vulnerable web application. It comes with a tutorial which goes through basically giving you a pretty good idea of where the defects are in the application, what they look like, what the generic mechanics are for those defects, how they work, and then gives you some pretty good guidance on how to fix them. So Zap's also got a Docker image, and I've created a Docker image for NodeGoat. So, and NodeGoat's got a dependency on MongoDB, which also has an image. So you can have these running in your nightly build, and that's the idea, right? So you have them running in your nightly build. So a developer introduces a defect today, and he comes in tomorrow, and he realizes that he's got a defect. He knows how to fix it, because the report that Zap generates actually gives him a lot of information. Plus the context is already in his head. Okay, so I need to show you just the test to start with. Okay, so this is the profile.test. We're going to be testing the profile route, which is basically the area that was defective that allowed us to carry out those exploits at the start. So we've got the Zap target app. Whatever it is, Zap target app. Zap target app here. So this is NodeGoat, and this is just taken from the environment files in there. Then we've got the Zap hostname, which is basically where Zap's going to be hosted. It can be hosted anywhere. It could be in a container or whatever. And then we'll move down a little bit. So we're using Mocha test framework as well in this proof of concept. We've got this test.before, which uses Selenium to fire up a web browser, and we populate these first 7 fields with some dummy data and proxy that through Zap, so that builds up the sites tree in Zap, so Zap now knows what our profile route looks like, and then we can tell it to start testing. So I used Selenium in this proof of concept because it's the easiest way to get up and running. You can just do all this via the Zap API, but it's a little bit more tricky. And you'll see all that you'll see that play out soon when the browser pops open. We've got this alert threshold here. So the idea here is your development teams inherited a brownfields project, and they set up some tests on it. They want them to pass to start with, so they're not waiting around in defects before they even get moving. So we set this alert threshold to whatever the number of alerts it has, and then we get a passing result from then on, and then any failures from then on we can go and fix, and then we can start to whittle away the alert threshold as well. And the most important part in this test is the sync.series. The other thing is, it's a lot to cover. So the Zap proxy here is a client library that we use to interface with the Zap API. There's a bunch of these for different languages, so we're just using the Node.js one. And if you keep your eye on the green function names, that's pretty much tells you what's happening in here. So we need to basically set up some actually, in this case, we use the default context, but you can set up a new context, and that's what I've done later on for another client. So we set logged in indicator and a few things in here that basically just set forced user. A few things here that tell Zap that when it comes across an area of our application that it needs authentication, how to authenticate and how to log in, and we give it the credentials and also forces it to log in. So I've got this. So this is the login string here, and somewhere down here we've got system under test username and password somewhere there. Oh no, sorry, there it is. System under test username and system under test password there. So that allows Zap to log in. And then we just I tell it to active scan our application. So the idea here is this is the profile test. We can just pretty much will swap out the text that says test the profile route, and then put in any other route in there, and so that we can use the same piece of code over the rest of the application without repeating ourselves. Okay, so, and then we basically just tell Zap proxy to active scan. It's quite a high-level scan. The idea is to do a high-level scan over your entire web application to start with to get reasonable coverage, and then start using some of Zap's lower-level features so that we can actually go deeper. This part here just gives us feedback as to how far through the scan it is, and this one here just tells Zap to write a report for us, and we give it a name. Okay, so let's see how this works. That's all right. So I've got to resize it, it's too big. Okay, so what we've got here is we've got the Zap UI. You can see the Zap UI there over on the left. It's here. We don't actually need it to be a UI, but I've just got this for demonstration purposes. So let's run that. Yeah. So okay. So we've just cleaned out. Okay. So we've got four squares there in our terminal, right? So we've just cleaned out the NodeGoat database so that we've got a good known start. Now we start NodeGoat. And in the top left pane there, we actually run the grunt test security, which fires off the Selenium web browser, fires through our initial requests, logs on. There. So that's logging in. That's Selenium doing the logging in and then populating their fields. You can see it built up the sites tree in Zap, just under here. And then we're into the active scan. And you can see the percentage of the active scan, that's finished, and we get the same percentage reporting here in our console. Okay, so the idea here, so we're just going to have a look at what the test results have told us. Okay, so it says we're finishing scan. Please see the report for further details. About to write the report. Tells us where the report is, and it says search the generated report for profile to see the 7 vulnerabilities that exceed the user-defined threshold of 3. So we're just going to pop open that report that Zap's created for us. Yep. So we're doing this, so we're searching on profile now, and we've highlighted the 7 defects that Zaps are reported on. So it's told us, it gives us quite a bit of information here. It gives us the URL that it's used to attack. It gives us the actual parameter that it's used and the attack. So it's given us enough information to actually to reproduce the attack. Okay, so the developer comes in the morning. He realizes he's screwed something up because he's got this running in his nightly build. He applies the fix. So if you're using NodeGoat, you can browse to the where NodeGoat's running from, and then the tutorial/AT route for some details on how to fix that cross-site scripting defect. So the developer goes in there, fixes defect, which eliminates the attack that we did at the start, where we used spear phishing and stealing passwords using our Facebook user. So what we've done there is we've just cleaned out the database again. We've restarted NodeGoat, and we're rerunning our test. And Selenium fires up our web browser, populates those fields, builds up our sites tree in Zap, and then we're straight into our active scan. And we're getting progress of how far through the active scan we are here. And it's a passing test. And we can go into that report. Let's just have a quick look at that. It's told us where the report is. Yeah, and these are just the initial 3 defects that are found in there. I'm getting kicked off now. Okay, so that's pretty much it. For that proof of concept, how to set it all up, you can work through my book. It's in my book, How to Set It Up, or just have a look at NodeGoat on my Binary Mist GitHub account, and it's got the directions of how to set it all up there. So that's it.